I basically I'm streaming from another place, and I will be doing this for the next weeks. So my setup is basically back to just one screen, and I seem to be able to only capture the browser for some reason. But okay, um, which is maybe not bad. Um, we'll just try to stick to the browser then, see if that works well. But yeah, essentially, what I've been doing in the past is focusing on like obsessively on this exercise, and I've gotten as far as just finding a solution that is almost like the one here. So what I will do is I'm definitely going to actually ask for some help, I think, because I've gotten there, but not with these exponents, just one half. And so there might just be a mistake here. There might just be some minor thing that I'm missing. So I'll see if anyone else can if someone else can actually help me understand where is that missing. Because I mean, at least I don't know. This at least it feels like um, I've been able to and to learn new things like the polar integrals and stuff like that, which I was not aware of. Um, yeah, so I mean, I'm happy that I actually try to go as deep as I could, and I did take something interesting out of these, something useful out of that. Now, we should kind of. I want to go back to the next sort of step in here, which is showing that the probability density of finding the particle with momentum h bar k is isotropic. So it does not depend on the direction of the momentum. Because the thing here is, so here there's a big step that was it's still unknown to me, which is the conversion between position and momentum, right? So here, and I really care less about the exercise results specifically, but what I want to understand is the logic of how are these things translated. So here there's a bunch of things, and so this is yeah, there's a bunch of things in here. Um, and I think that doesn't depend on the result of A because they still use N. Um, so we have taken the z-axis of integration variables to coincide with the momentum direction. Hmm. So what do they? Okay, so what do they want to? So what is it that they're asking? They're asking whether so the probability density of. So first is two things. First, I need to find a way to convert that, um, a way to convert that um, to the momentum stuff. Which here they do something like that, which it's weird. This is something that I really don't understand, but they seem to just be translating something here. Like let's see, they just seem to add this thing here, the n of, so there's some kind of like, it almost feels like it's just a kind of a multiplication, which if we think classically, momentum definition, um, what is a simple definition of a momentum? Momentum position conversion. I'm definitely interested in the classical things first. Spaces. You're catching that up, right? Yeah, yeah. Actually, it's cool. Actually, to just use the browser, maybe that's even easier. Um, position space and momentum space. Quantum mechanics and classical mechanics. So let's see. Exactly, because it's definitely something about there's definitely a sort of a derivative association to it, right? Because in a way, the fastest sort of the speed in which you change your position, it's somehow proportional to the momentum. Because momentum is, first things first, I understand what's the relationship between between the two variables, and momentum is really just something that's it's velocity, right? It's just velocity times the mass, but let's just ignore mass for now. So it's literally velocity. So it's the derivative, really. So it's funny because if I look at the solution, it almost seems like this is what's happening here in a way. There's some weird renaming happening here. Okay, because there's R, but then there's this kind of factor added to it with X. But in essence, it's like there's a triple derivative of X because X is because it's position. So then there's this funky thing here. But essentially, it's just as simple as, okay, wait a second, but there's an integral. What are we integrating over, though? Why? Because it's a sum, it's an infinite sum of what? I'm not so sure why you have to do the integral, though. But I mean, in Lagrangian mechanics, so canonical momentum. Hamiltonian mechanics. It is essentially it is essentially velocity, right? I think in quantum mechanics. As an integral. So suppose we have a three-dimensional wave function in position space. Then we can write this function as a weighted sum of orthogonal basis functions. It is clear that if we specify the set of functions psi k, say, as the set of eigenfunctions of the momentum operator, and the function holds all the information necessary to reconstruct psi r. Whoa, 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 whoa. Okay, so the momentum operator. Oh, look at this. So this is what's being applied there, I guess. This here. Square root of 2 pi. Yeah. So that's really it. Okay, so this is just a prescription. Okay, so just put this in here. Whatever that is, whatever that is. Okay, so that's the general thing. I'm not so sure I intuitively understand why. The eigenfunctions are these. How is that derived, though? Okay, so suppose that we have a three-dimensional wave function in position space. then we can write this function as a weighted sum of orthogonal basis functions. This is what's a bit. This is what's a bit. This is what's a bit abstract, right? But it's kind of the same idea, just translated to functions. It's the same idea of like, you know, I can have a vector, right? And I can just also write that vector as a function of the sort of a basis, and then some weights to it. I can always do that, right? I think just this is something that you can do with functions as well. I just have to accept that in a way. It's a bit. This is quite abstract, right? But it makes sense in a way. It's like everything. I don't know if it's something. Yeah, it's funny. I don't know if it's something that it's always true for every kind of construct. It just even for functions, right? So it's quite crazy. The concept of eigenfunction is quite crazy. An eigenfunction of an operator is a function such that the application of on gives again times what the an eigenfunction of a linear operator. S not as a function in that space that when it's upon by d is only multiplied by some scaling factor. Yeah. It's just in a way what you're saying is everything is there's always sort of a reference to anything, to everything, and so you can always write something as it doesn't matter if it's a vector, it's a function, it's whatever it is, right? And that is what this eigen stuff is about, and that is essentially what an eigen and what sort of the eigenvalues, what the eigenvectors of a matrix are. If you assume if you understand a matrix, it makes sense as in like if you understand a matrix as a function, right? Or as a transformation. There's always yeah. So essentially, this is always like everything can be decomposed kind of story. So with a function is the same. So what you're saying is let's assume we have a wave function, and let's assume that we can write this function as a weighted sum of some orthogonal basis functions. So you have this psi j eigenfunctions which we don't know about, and then it's a sum of these. Or in the continuous case, there's the integral, and that's where the integral comes in. Okay, so you have this integral, and then you have these coefficients in here. Cool. D3k, D3k. I'm not so sure what this k space in here means though, but is it clear that if we specify the set of functions psi k are, say, as a set of eigenfunctions of the momentum operator, the function this function holds all the information necessary. That's true. Okay, so the coefficients of these hold all the information necessary, but I'm not so sure. Yeah, to reconstruct these momentum of the momentum operator. So in essence, what you're saying is the momentum operator. So it's an alternative description of the state. Psi. In quantum mechanics, the momentum operator is given by these. So you have this momentum operator, and so these are the eigenfunctions. Okay. So, so essentially, what you're saying is, okay. So these are so what you're doing is calculating the eigenfunctions. However, the fuck would you do that? Eigenfunctions of momentum operator. That's something interesting to look at. Functions of momentum. So eigenfunctions of momentum operator. And so that's definitely something I want to take a look at because I want to understand how we get there intuitively. I know that's damn complicated, but it's eigenfunctions of momentum operator. That's where I definitely want to step in next in the next session, hopefully tomorrow or something like that. So this is where these things come from. But then how do you put things together? So then you're saying, okay, so these are the eigenvalues. Okay, but you then still have these. How do you plug in? How do you? Hmm. And we see that the momentum representation is related to the position representation by a Fourier transform. No, really? Ugh. With eigenfunctions. And so what do they do here? Is they say, what the heck? Okay. Am I looking at the? Am I looking at the? Am I looking at the opposite transformation? I think so. Yeah, that's what I want. I think that's definitely what I want. Yeah. Okay. Okay, so you're looking at, so you're saying, okay, so something that's in momentum space can be expressed as a weighted sum of orthogonal bases. Boom. And so you're saying this is, so you're just saying, um, uh, okay, so you're taking the eigenvalues of the position operator. So that's what we want to look at, not the momentum operator, because that's the, so position operator eigenfunction. That's what we're going to look at. At least in a way, at least trying to understand these, because that's what he is. That's what you're saying. So you're saying you take the position operator and find the eigenfunctions of it, and then express. So these are the eigenfunctions, and saying what you're saying is that which turns out to be the inverse Fourier transform. E minus IKR, and that's where, yeah, so that is where this comes from, because this is basically E times, like, you know, this is alpha function times this thing here. So this is where this is coming from. Yeah. dr blah blah blah. So d3x x. Okay. dr d3r r space. And then they do some kind of funky stuff in here. They say, okay, that's more or less these. and then we square that, and yeah, okay. So then the next step is, and so the first step is understanding how that switch, and I think now, like, what's confusing is the whole thing about about Fourier transforms and whatnot, because it's like people, I don't know, you tend to find that online, that it's somehow, for some reason, I always thought it just, you do some kind of Fourier transform or something like that, but this is just intuitive in the sense that what you're doing is you're expressing it using the eigenfunctions of another basis. Uh, hmm. But yes and no. I'm not entirely sure that I understand this though. Why would that give me? Why would that give me momentum? It still somehow depends on. Okay, that's not dependent position because you're integrating over it. But then what does it depend on? You know what I mean? That is a funky one. I would never be able to do something like that. Oh my God. Oh, Jesus. Nice. Is that the entire? Oh no, that's E. That's something else. Okay, so this is where. What are we doing? First of all, we're doing. No, we're doing B. Sorry. Okay, so B is these. Oh, it's just until here. Okay. Uh, okay, so they do get to something where it's like it depends on the mass, and then some kind of like, and time. Oh my God. That's what I don't understand. Is like how, like, that still depends on R. So you're integrating over these, but then it almost feels like it kind of turns unitless. So I don't really know. I don't really understand. Uh, as a function of what? Like, how do you? Yeah, I'm not so sure I understand that. So maybe what I should do is I should actually just go through some more specific version of these. Okay, I think I understand the three-dimensional wave function in momentum space can be expressed as a weighted sum of another orthogonal basis function, a set of functions. Um, and so, and then you take the position operator. I'm not so sure I understand the intuition behind, like, why does these work? But okay, it's one step a little bit forward.